Good afternoon, and welcome to this special astrophysics colloquium by Professor Walter Lewin. The mission of MIT is to advance knowledge and educate students in science, technology, and other areas of scholarship that will best serve the nation and the world in the 21st century. Few people can embody that mission in one person. Walter Lewin is one of those very special people. Walter, of course, is the most famous physics lecturer that MIT has ever had. In addition, he is the father of much of contemporary X-ray astronomy, the study of exotic phenomena in accreting neutron stars and black holes. He received his PhD in 1965 from Delft University in the Netherlands, and at the beginning of the following year, he came to MIT as a postdoc in the lab of George Clark, and quickly became an assistant professor. He began studying the skies using balloons to carry aloft X-ray detectors to measure cosmic X-ray sources. The 1960s, as we will hear in this lecture, were a golden era for the discoveries made using new technologies in space and at the edge of space, the top of our atmosphere. In the 1970s, he played a key role in the SAS-3 satellite mission, including the discovery of the rapid burster, an amazing object which emits flashes of light of X-rays more than 5,000 per day. Nowadays, we talk about cosmic gamma ray bursts as being the fascinating phenomenon in the universe. But from the entire universe, we see perhaps one gamma ray burst per day. This object was emitting 5,000 X-ray bursts per day. In 1974, Professor Lewin became a full professor and continued his pioneering studies of cosmic X-ray sources, including in the 1980s the discovery and the study of quasi-periodic oscillations arising from the accretion disks of matter swirling in the very strong gravitational fields of neutron stars and black holes. Indeed, he became one of the experts in applying these measurements to testing general relativity in the strong fields produced in those objects. In more recent years, Professor Lewin has become famous for his physics lecturing. Many of you have seen his lectures. Perhaps some of you were fortunate enough to attend the special lectures he gave this summer for Japanese television on his physics, electromagnetism, classical mechanics, and waves, the beauty of music, the beauty of a rainbow. In fact, I would expect that many of you have read his book, For the Love of Physics. If not, please do. I've read it from cover to cover, and as he says in his lectures and in the book, it will change your life forever. He's received many awards for both his scientific research and his teaching contributions, including the NASA Award for Exceptional Scientific Achievement, the Buckner Teaching Prize of the Physics Department, the Baker Award of MIT, and many others, including last year being selected by Princeton Review as one of America's top 300 professors and the only one from MIT. Professor Lewin has been an inspiration to me personally as far as integrating teaching and research. He exemplifies the very best in everything he does. I know that for this one lecture today, he practiced 4 or 5 times, including at 6 a.m. this morning. So I hope that you are still full of energy, Walter, as always, and I look forward with the rest of the audience to your wonderful lecture to come. Please welcome Professor Walter Lewin.
I've been on many oral committees whereby we tested the students on their knowledge on astrophysics. And I typically would ask, what do you know about X-ray astronomy? Don't bother me with the sun. I want to hear about extrasolar X-ray astronomy in the range 1 to 10 keV. A student would say, well, there are about 100 very bright X-ray sources in our galaxy. They're binary systems, many of them, with a neutron star and with a black hole. And there's mass transfer, and potential energy is converted to kinetic energy. It gets very hot, 10 to the 7 degrees, and you get X-rays. Quite impressive. But I say, tell me a little bit more about these binaries. Tell me are they variable in time? And then the student says, oh, you won't believe it. Millisecond timing, weeks, hours, years, anything has been observed. And he said, and the worst of all is, there are X-ray sources which pulsate. They have a period, rotating neutron star. Well, I was always very impressed, but I would go a little bit further, and I would say, how about galaxies? Are there any particularly bright X-ray galaxies? Student says, yeah, you better believe it, very bright ones. We give them a name, we call them AGNs, active galactic nuclei. Well, time was running out, but I still wanted to go a bit further. How about clusters of galaxies? What do you know about the clusters of galaxies? Students would say, well, that is a fantastic story, because there is hot gas which is trapped in the potential well of the cluster. Not well understood why, and that's 10 million degrees hot, and so that hot gas emits X-rays, and the mass of that hot gas is often much larger than the mass of the galaxies. Well, before I finish that exam, I would say, is there such a thing as a diffuse X-ray background, like the 3-degree cosmic background radiation coming from all directions? And now the student begins to hesitate. Yeah, the student said, yeah, there is such a thing. I said, does it come from all directions? Yeah, he thinks it comes from all directions. I said, from how far does it come? Is it nearby or is it very far away? Clearly, the student doesn't know. But he did so well, he passed. Now, most of you probably knew all this. And if you didn't, then I would say try hold on to it for only 1 hour. And then you can forget about it again. And I want to talk today about how all this came about, how it was discovered, and I restrict myself to 10 years, the first 10 years of X-ray astronomy, 1962 to 1972. Edward Hurlbut suggested in 1938 that the E region of the Earth's ionosphere was partly caused by X-rays from the sun. And in 1948, attempts were made to detect the solar X-rays by Burnite and Tousley, and they used V2 rockets, which were developed in Hitler Germany by Werner von Braun. Werner von Braun used slave labor from concentration camps. 20,000 people died. Werner von Braun was a war criminal, but later in the United States, he became a hero. And that still puzzles me. Rockets were seized after the war, and both Burnite and Tonsley believed that they had actually detected X-rays from the sun. But it was a little bit ambiguous because they had no directional information. In 1949, Herb Friedman of the Naval Research Laboratory conclusively demonstrated that the sun indeed emits X-rays. In the summer of 1959, Bruno Rossi, who was a professor at MIT, chaired meetings of the Space Science Board, and among the topics that were discussed was X-ray astronomy. And Bruno went to his ex-student, Martin Ennis, who was at that time the president of American Science and Engineering, but very close here in Cambridge. Bruno was the chair of the board. ASNE was involved in investigations of the effect of nuclear bomb explosions in the upper atmosphere. And Martin was very enthusiastic and willing to commit resources for X-ray astronomy. I'd like to show you a picture of Bruno. And you see Bruno Rossi here together with Beppo Occhialini, Italian. And what is so special about this picture, that both men got an X-ray observatory called after them. The Bruno Rossi Timing Explorer and the Beppo Sachs Observatory, which was the Italian one. Riccardo Giacconi had joined ASNE early in 1959, and in September that year, Bruno Rossi discussed with Riccardo to explore X-ray astronomy, and Riccardo picked up the ball and he ran with it. He explored various avenues into X-ray astronomy, and they first, together with Bruno Rossi, George Clark, and Stan Albert, all at MIT, they wrote a report in which they evaluated the possibility of X-ray sources. And they mentioned the Crab Nebula. That's a supernova remnant at a distance of 6,000 light years. And they also mentioned the moon. Nice and close. X-rays from the sun could be scattered off the moon. If you place the sun at a distance of 100 light years, there is no chance on Earth that you will be able to detect it in the early 60s with the available detectors. You were short by 8 orders of magnitude. So the odds were very, very small. So Riccardo explored the possibility of concentrating X-rays in order to get a higher sensitivity. And in 1960, he wrote a joint paper with Bruno Rossi in which they used parabolic mirrors, grazing incidence, X-ray optics in order to improve the sensitivity. And you see here the paper. The paraboloidal surfaces are here, and the idea of nesting them, more than one, was Bruno's idea. And so the X-rays come in, and here's grazing incidence, and here they come together, and that, of course, would enormously improve the sensitivity because you would have much lower background. Hans Walter had studied the problem of X-ray emission a decade earlier in an attempt to develop an X-ray microscope. In his case, the X-rays are reflected twice. Grazing incidence first of a paraboloidal mirror and then of a hyperboloidal surface. It was very unpractical for microscopes, but Riccardo recognized its usefulness for an X-ray telescope. And by 1965, he had built one, designed one, and tested one, and published one, typical Riccardo. Riccardo also realized that it would take a long time for these mirrors to be built, and so he explored the possibility of developing large area Geiger-Müller counters. That was done at ASNE by Frank Paolini. They were supposed to be large, and they were going to have what's called an anti-coincidence shield. Bruno Rossi is the inventor of the anti-coincidence circuit. And what this anti-coincidence shield does is very important. It discriminates between X-rays and cosmic rays, so it keeps the background down. Proposal was sent to NASA. Turned down. Proposal was then sent to Air Force Cambridge Research Laboratory. And Riccardo made some changes in the proposal. He stressed the fluorescence of solar X-rays from the moon. I suspect that he suppressed the Crab Nebula as the Air Force may not have been too interested in something that is 6,000 light years away from us. But the moon is 1 light second. That's within striking distance. the proposal was approved. The first rocket flight was in June 1960. The rocket failed. A second rocket flight in October 1961, the doors of the rocket wouldn't open. And the successful flight came on June 18, 1962, from White Sands. Herb Gursky, who had joined ASNE a year earlier, was present during the launch. Ricardo was not, because Ricardo was involved in the bomb testing business of ASNE, so he was not present during that launch. They launched 1 minute before midnight on June 18. There were 3 large area Geiger-Müller counters on board. Large area in those days was the size of a credit card. So they had 3 Geiger-Müller tubes about this size. The rocket was 6 minutes above 80 kilometers. It had no collimation or whatsoever. So the field of view was 2 pi steradian, and the rocket would rotate 2 revolutions per second. And they detected a signal, loud and clear. But of course, at first, there was great concern. Were these really X-rays? So they scrutinized the result as much as they could. They tried to explain them away, but they did not succeed, and so they decided to publish. It was published in PhysRev Letters in December '62, and the title was Evidence for X-rays from Sources Outside the Solar System. And in that article, they mentioned that they also had discovered what they called diffuse X-ray background. That's the thing that the student had problems with. Diffuse X-ray background. The editor of PhysRev Letters was Goudsmit. And Goudsmit called Bruno one day, and he said to Bruno, "Do you really believe this? Do you really believe that this is an X-ray source outside the solar system?" And Bruno says, "I happen to be co-author on that paper." Goudsmit said, "Yeah, you're right. We'll publish it." I'll show you here a picture of Ricardo together with Herb Gursky. They were not yet at ASNE. This was in 1958. At that time, they were together in Princeton. And here then comes the most important paper ever written in X-ray, extrasolar X-ray astronomy, which is that discovery paper. And if we look at this, then on the left here, you see the counting rate in X-rays, and this is 360 degrees in azimuth, so that's the whole horizon. And you see 2 curves. One detector failed, so that's why you see 2 curves. The curves are not identical because the thickness of the windows of the 2 counters was different. And there is just no question that there is at least one source here. And it is not the moon, because then the peak of the source would have been here. And this is what they called the diffuse background. In all directions where you looked, you would still see X-rays. This here is the entire sky above the horizon when they flew the detector. And they put the source in this error box, 10 by 10 degrees. That's the best they could do, which is an amazing thing if you have no collimation at all, a field of view which is as large as the sky, and you still make the commitment that the source would be located in a 10 by 10 degree area. What you never read in the literature, in not a single book, that they were off by 25 degrees. Because later it was found, and you will see why and how, that the source is here. When this was published, of course, it was an A-bomb explosion, and Herb Friedman at NRL immediately flew an X-ray detector in April '63, and he pinpointed the source and found that it was in the constellation Scorpio. The 10 by 10 degree box is so large that there are at least 2 stellar constellations, but maybe even 3 in the 10 by 10 degree box. Therefore, in that discovery paper, they could not identify the constellation. And the constellation is not identified in that paper. Even though Ricardo, in a book that he recently wrote, claims that they found the source in SCO X1, which is not true. So now comes the question, what are these objects? Are they optical counterparts? The X-ray luminosity must be phenomenal, but even if you put the source as close as 100 light years, which is next door, right, then they would be at least 8 orders of magnitude more powerful